difference, but
Okay. I'm glad you guys still alive. Look at the schedule here for the assignments. So tutorial 5 and homework 5 is a little bit better, so you have more time to work on it. I think tutorial 5 is due next Monday, I think. Yeah, Monday. And then homework 5 is Wednesday next week. So we have today, Wednesday, Friday, and Monday to work on the problems in homework 5. Which makes sense because a lot of new methods will be introduced. And you see, we only have, I shouldn't want to say only, but there are like 11 tutorials and homework assignments, but we have like 16 weeks in the semester. So I think it's just making you guys super busy at the very beginning, and it's gonna slow down a little bit later. Okay. So for today, we are going to work through the last problem on homework 4, which is due tonight, right? And work through that again one more time. But since I figured out we don't need that many equations, we just reduce the number of equations. If we just calculate the power for one component on the left-hand side, we really don't have to list so many equations, right? We'll see if we can figure that out. And then we'll move forward with tutorial 5. Right. Let's do it. Equations we need for this guy. So Vx over 2 is a current going down, going into it, and giving us two currents flowing out from V1 node. So this equals Iy plus V1 over 25, right? So now we got 3 variables introduced. V1 minus V2 is what? V is, I have 10 volts here. So we got a Vx introduced, so we need to address this one so we can help with solving for Vx over here. So here's Vx, here's V2, which is great. So V2 is what? V2 is what? Come on, word diggers. V2 is what? Oh, V2 is Vx. We got a Vx here introduced, right? We got a V2 introduced. Why not just directly use it, right? V2 is what? Vx. So we got a V1, V2, Vx, Iy, 4 variables, 3 equations, just got one more. Which one we can use? Let me see. We probably have to keep moving to the right. Let me see if we have to. Maybe. Really? We have to keep moving to the right? Let me see Storm over here. Oh, you are here. Right, which one did we use during office hours? I mean, oh, it's okay. What's your question? Oh.
The I plus V2 over
Which one?
IY equals the given Y. So like, yeah, that one.
Yeah? Oh, equals this plus this. Yes, that's right. One going in, two going out, right? So IY is what? V2 over 5 plus, this is given, 23 amps. Done, yeah, only 4.
Do we not need to find the other two, the critical nodes?
Where? Here?
Yeah.
Yeah, because asking for the power for this guy.
Oh, we're just asking the power of that?
I think that's the problem. What's the problem asking for, right? Oh, you haven't done that yet? Jeez, it's due tonight.
Yeah, that means due tonight.
Yeah, so work on it at 10 p.m. Perfect.
I'm doing it tonight.
All right, but homework 4 is not too bad. Only 5 problems. 6 problems. Okay. This simplifies things a lot. Okay, that helps, right? Let's just do this. Okay, we don't have to like list 8 equations. You want me to solve for that? You have the calculators, right? So you can put all the equations inside. But definitely you have V1, V2, Vx, right? Iy. 4 variables, 4 equations. Will definitely do the job without any problems. And then you got Iy, right? So Iy is pointing into that anode. So you are if you directly use Iy times 10, you are getting the power absorbed or developed by this guy. It's flowing into it, right? It's charging up the battery, so it's actually absorbing. If it's asking for the power developed by that 10 volts or whatever voltage you have on your side, right? The power developed by this guy, you have to add a minus sign in front of it. So this current, you calculate it over here, times the voltage, and add a minus sign in front of it. Okay, any questions on this? Good? Right. Let's do the problems in tutorial 5. Tutorial 5. It's almost halfway through it since we have 11 tutorials in total. I think 11 tutorials, 11 homework assignments. So this teaches you about source transformation. So this is pretty simple. This one is really simple because what's happening is if you have a voltage source here, keep it open loop since we are trying to design a circuit to serve or to drive that load. Keep in mind that's what I'm talking about this, okay? Here's a load. It could be a resistor, could be a capacitor, could be anything, could be a motor. Okay, it's just a load. A load is being put in the box. So when we work on the source transformation and all the equivalent circuit problems, you'll see a lot of these problems in tutorial 5 and homework 5. We have to remove the load to analyze the circuit. So keep in mind, so the load is the load, circuit is the circuit. So imagine you are an electrical engineer being asked to design the circuit to drive that load. Okay, so you always remove the load. It's like this, right? So you remove the load and plug in yourself and replace the load over here and looking at the circuit to the left. That's what's happening, right? So if you're looking at the circuit from right to left, this part of the circuit can be converted to a current source and a resistor in parallel. With the open circuit here as well. So you remove the load, right? You're looking at a circuit, see what the circuit is going to do to me, right? Just looking at it. Doesn't matter what the load is, right? So this circuit is going to deliver a certain voltage at this point. Okay? So you can convert it to this. And this is called RTH, in general, RTH, and this is called a VTH. The reason is TH is because it's called Thevenin's equivalent circuit. It's probably the guy who invented his last name, equivalent. Thevenin's equivalent circuit, so that's why it's a TH, RTH, VTH. You can convert any DC circuit into this. Just a voltage source and a resistor in series with it. So we are going to learn how to do it for in tutorial 5 and homework 5. That's a job, that's a task over here. Okay, same thing. This is called IN. It's called RN. Why is N? Because it's Norton's equivalent circuit. Equivalent circuit. So any DC circuit can be converted into Norton's equivalent as well. Right? So we're going to learn how to convert any DC circuit with all the resistors, dependent source, current source, voltage source, and merge everything together and convert into equivalent circuit like this. So when we talk about equivalent circuit, it's usually in terms of what? In terms of what? Equivalent to what? Or equivalent for what? For doing what? For example, you have a super complicated circuit, looks like, not super complicated, but something with a lot of meshes, like this, right? Okay? Something like this. And eventually you convert it to this. Okay? For what? For driving the load. Because the load is a customer. It's a customer. So the customer give you a load, right? You are an electrical engineer to design a circuit to drive the same load. And that load, to drive that load, you can use this circuit, or you can convert everything to the equivalent circuit. It's going to be the same voltage appear here to drive it. So you can see this one, you got the load removed already, right? So it's just an open circuit. You can connect your load to it. Any load, can be a motor, can be a resistor, can be a capacitor, can be anything. This is your design, right? Just keep it open. So is there any current flowing through this if you remove the load? No, because there's no, it's not a closed circuit. It's open circuit. No current is going to flow through it. Okay, this is grounded. All these are coming back. Okay, but nothing is going through this one because the load is removed. But if you plug in your load in here, you'll definitely get a current flow through it because the load is going to connect from here to here and flow current to the ground, right? But now if you remove it, there's no current. Okay. So you can convert the circuit into this, or you can convert the circuit into this, just one single current source in parallel with this resistor. However, there are some conclusions, and you can convert in between these two circuits as well, which is RTH equals RN, which makes things a lot simpler. If you calculate RTH, you'll know what RN is since they are equal. Okay. So now let's learn how to. Another thing we have to know. So for force source transformation, VTH over RTH equals IN. So if you got the equivalent circuit with the Thevenin's equivalent format, right, and you can easily find out Norton's equivalent by doing this. So VTH over RTH, if you got this, right, you can convert it into this by using VTH divided by RTH. You got this, right, and the resistor is not changing. Same thing, if you convert it back, you just use this current times the resistor. Ohm's law, very simple. You got a VTH, and rotate this resistor to the top and make in series with the voltage source, like this. Something you have to memorize at the very beginning to lay some groundwork for the future tasks. But is that clear? These two circuits are really simple, right? These are finally we want to convert all the DC circuits into the equivalent circuit like this. Why it's important? It's when you are doing some other advanced circuit design, you will find out this is very important. So now you can convert it here, and you can convert in between these two circuits by using these two equations. Okay, so IN, if you have this, IN times RN will be VTH, right? And then you just put the same resistor on the top. Let's see some examples. You can do it. Okay, here. Let's do the source transformation stuff. So first, these two can be converted to what? A voltage source in series with a resistor, and the resistor value is not changing. So the voltage source value will be 8 times 75, right? So these two can be easily converted to this. Okay, remember? All the following circuits can be considered as a load. Can we? That's 2 terminals here. So all the rest is just a load. Remove it. Just looking at this part. Why? Because we are just replacing this circuit as these 2 terminals with another circuit, also the 2 terminals here. Just replace it, right? Move it. So you can exactly fit in here as well, right? It's 2 terminals, no difference. So everything else is just a load. You can definitely use this one to replace these 2. What is the voltage source? 8 times 75 volts, right? What's the resistance? It's not changing. 75. Okay? Easy. What about here? Immediately you see 125 ohms resistor. What you want to do? Just add it. Just add it. Now we are here. Okay, we are here right now. Can you add it to it? Sure. It's just a series resistor. So what's the value for this big resistor? 200 ohms, right? So you can convert anything before these 2 nodes to this. Just 1 voltage source and 1 big resistor, 200 ohms. Any questions so far? Good, right? No, not good. So see here what we do. If you have a current and a resistor in parallel, right? So we can easily convert it to this. No problem from here to here, right? And so now we need to find out the values for this and this. This is the same as this, and this is going to be this current times this resistor, right? This part to this, and this times this got this voltage, and resistor not changing, put on the top. So replace these 2, and comes here. You got another resistor in series, 200 ohms. Now arrives here. Okay. Now you are seeing a voltage source. What would you like to do with it? Source transformation or something else? So again, why I talk about the load and the customer stuff at the very beginning, because we're always treating the following circuits as a load or the customer, right? So we don't really want to get everything here engaged when we doing the transformations. You just remove it, and then you look at this part. Now we are arriving here already, right? What is the equivalent voltage being provided to these 2 terminals? Don't worry about whatever going in here, and this is on the left hand side of this or on the right hand, doesn't matter. It just overall it's going to give you effective voltage across these 2 terminals towards the customer, right? The customer, the load. So now you just look at this part. Don't worry about anything here. It's a disconnect circuit for now. Okay? What's happening here? How would you like to transform it? You want to transform it, convert it to a current source. If you got a current source and resistor in parallel, right? You got these two, definitely you can convert it to this, right? But does it help? You convert it to this, you use something like this, replace with this one, and you immediately see a voltage source. How do we deal with that? It's probably better not converting it for one more time. I just look at the two voltage sources, and it's going to give you an effective voltage overall. Okay. How and why? So what is this voltage? Is that correct? 600 volts, right? This guy is 600 volts, and this is 200 volts. It doesn't matter if the voltage source is here or here. It doesn't matter.
Could you explain that further? Because like, doesn't that change the current flowing through the resistor?
No, because we remove the load. Just internally, it's not changing. Why it has to change? It's just like a potential, like a force. It's the same, still the same branch, right? It's the same branch. You're flowing water into the pipe. You can give the pressure here or give the pressure here. It's just overall giving an overall potential difference at the output. The pressure could be applied over here, could be applied over here. It's not going to change anything. Let me see what we can do further. Let's just draw it, okay? So for example, here is 600 volts, right? Okay. Let me see how I can explain that to you guys. The load is removed, no problem on that, right? Is there a current going through it? No, load is removed. Okay? So what's the voltage here? 600 volts. What's the voltage here? The power supply is going to drop it by what? 200 volts. Why? Because it's plus minus, right? So whatever voltage here compared to ground will be dropped by 200 volts. So what's the voltage here compared to ground? 400 volts. Is there a current going through it? No. Load is removed. So what's the voltage here? 400. Right? Okay? So for this one, (600 volts, 200 volts). Is there any current going through it? No, it's disconnected. Load is removed. No voltage drop. 6 volts, 600 volts, 600 volts, right? And drop by 200 volts, you're getting 400 volts here. So it's not changing anything. Right? So in that case, we always deliver a 400 volts at the terminal to the load. Since like I said, we just remove the load, and if you replace the load with yourself, like you standing there looking at the node here, right? So no matter how you position them, you always see a 400 volts at the terminal. Does it really matter? You just see for the load, it just see just looking at this 400 volts, it's always 400 volts. It's not changing anything, right? So you can definitely, if you see something like this, feel free to swap it. If you don't want to swap it, it's okay. Just use this method to analyze it. But anyway, so eventually the effective voltage source in this circuit becomes what? You could consider this as another, it's a new method for you guys to analyze. When you see something like this in series, you can always combine these DC sources. Okay? So it's definitely, this guy is pushing back. It's pushing back the potential or the force or electric field back. Right? So this is 600 volts. This is 200 volts. You're getting this part. Eventually, you're getting 400 volts to this point, right? 400 volts. What is this? 200 ohms. So this whole thing can be converted to this. Okay. Then what's next? What's next? Looking at this point, you have 800 ohms. What should we do? If you convert these two guys into a current source and a resistor in parallel, and you can combine these two parallel resistors, right, to simplify things a little bit. And then convert it back, you can move the resistor on the top, and then combine with this one. So eventually will help. So now let's see what's going to happen if we do that. So convert these two into a current source and a resistor in parallel, right? So we use this voltage divided by this resistor to get the current source. And that's 2 amps, right? 2 amps. And the resistor doesn't change. Oh, no. Resistor in parallel. Okay, it's 200 ohms. And 800 ohms. Okay? So these two can be combined. That becomes 200 times 800 over 1,000, which is 160 ohms. So you got 160 ohms for these two parallel resistors, and then you convert it to a series voltage source again. So it's gonna be this times this is giving you 320 volts. The resistor doesn't change, 160 ohms. I got another 160 ohms over here. 2 amps. 128. 480, 2 amps. So it's still 160 ohms, same voltage, same resistance. What's next step? Can combine these two.
Since we combined the 400 volts and the 200 ohms into that current source, why do we still have 200 ohms in the circuit? In the going from the top to the middle diagrams we have
Here?
Because didn't you combine the 400 volt battery with the 200 ohms, so we got current source? Why do we still have 200 in parallel with 800 if we made it to the current source? Well, maybe I'm not understanding it.
Why we are getting here?
What do we still have 200 in that one since we have a current source?
Yes.
Shouldn't the 200 be in the current source?
200 and what? 200 and what with the current source?
Would it be in the current source? Like, isn't that why we write it we wrote?
Yeah, these are in series, right? So converted to here is in parallel,
Oh, okay.
right? Like we. Thanks for stopping me because I'm moving to the wrong direction now. it's good. So let's look at it. But now whatever you said was right. But moving to here, we shouldn't move to here. We should stop here and merge these two current sources. But never mind. Let's go back. Come back here. Remember, you have a 1 voltage source in series with 1 resistor, right? You can convert it to this by doing what? By doing this divided by this, Ohm's law, get a current. Never think about why it's not the voltage across this guy. Why you can use this voltage divided by this? You're getting this current. It's not the time to do the Ohm's law. It's just the method. I mean, you can eventually use some other equations, which is super long. I was looking at how to prove Thevenin's and Norton's equivalent circuits. I was Googling. I never learned it in undergraduate. I was Googling. That was super long, like 10 pages in Wikipedia. So I'm not going through that since I don't know how to do it. And I don't think that makes sense. So let's just remember here, Thevenin's and Norton's equivalent circuits. That's how we do it. And they are very easy to remember as well. Even though VTH is definitely not the voltage across RTH, right? Why you can use VTH over RTH to find out the current? It's just a method. Remember this, okay? Remember this. All right? This divided by this, you got this current in this equivalent circuit, okay? Doesn't mean VTH, the voltage across it. No, it's not. VTH, the voltage here. The voltage here. And we remove the load, so there's no voltage across it actually. There's no voltage drop because there's no current. Okay? Just remember these two pictures and seal this in your mind. It's just like voltage source in series with resistor, open loop. Okay, open loop. Current source in parallel with the resistor, open loop. Just these two pictures. Take a picture and seal it in your mind. They are equivalent. All right? And you can convert it in between these two circuits. How? Same resistor and Ohm's law to find out the current. You can use current times this to get a voltage. Either way, okay? And now we were here, right? We were here. And why we got here? Because these two are in series, like a VTH and RTH, right? So we convert it into a current source in parallel with a resistor like this. And we didn't change anything for the rest of the circuit. Nothing has changed, okay? Why we want to do that? Because if I put this one down here, I can get a parallel resistor. I can cancel this one. Not cancel, but I can combine with this one to get a new resistance. All right, so this one, I calculate it. It becomes 160 ohms. However, I probably don't want to going into this step. Do I want to do that? Oh, I should. Let's do it. Let's do it. Yeah. Since we're going to combine this resistor, so we're not making any mistakes. So this one, you got 160 ohms for the equivalent resistor, right? Imagine that this whole thing is going to be a 160 ohm resistor. So you can keep moving forward. You can convert this one to a voltage source in series with a resistor by doing Ohm's law. Even though 2 amps is not the exact current flowing through this 160 ohms resistor, but that's just the method, like what we said over here. Okay, if you got a voltage in series with a resistor, you can convert into this format by doing Ohm's law, by doing a division, not Ohm's law, by doing a division. Okay. Here we combine these two by using 2 amps times 160 ohms. You got a 320 volts for this voltage source, and then you move this 160 ohms resistor to the top, keeping them in series. That's whatever you replaced. This whole thing replaced by this. Okay? And then adding the rest of the circuit into the equivalent circuit. So got two 160 ohms resistors. What we can do for the next is so these two are 320 ohms, right? So you can transform these voltage source and resistor in series into a current source and resistor in parallel. What is the current source value here? 1 amps. Why? Because it's 320 divided by 320. 320. Yes, 320. And the resistance is not changing, so 320 as well. So what's next? Yeah, can we move these two in here? Are they adding to each other or subtracting? Adding. Why? You got two water pipes, right? Merging, right? Merging. Two water branches. So it's giving you what? 3 amps. You can easily shift this one here, right? So you got two current source. And then 320 ohms. 480, 128. What's next? Combine. Yeah, so eventually you're getting this 3 amps and 320. Oh, let me see. Oh, that's 98 ohms. I'm joking, I don't know. 320 in parallel with 480 in parallel with 128. Okay? But definitely you know it's going to be less than this guy, right? Some kind of experience to let you guys know. So you got a 3 in parallel resistors or any number of in parallel resistors. So the overall resistance will be lower than what? Will be lower than the smallest one. So if you see like 320, 480, 128, you can estimate the resistance is probably something like 90 something ohms. Okay, it will be lower than this one. Depending on the resistance of the other ones, if you got a huge resistor, like 1 megohms in parallel with something, the estimate will be very close to this, the smallest value actually. So for example, you have 1 ohm in parallel with 1 megohms. What's going to happen? What's the overall resistance? 1 ohms. Why? It's 1 times 10 to the 6 divided by 1 plus 10 to the 6. Ignore it. Cancel. What's the resistance? 1 ohms. So if you have a 1 very tiny resistor in parallel with a huge resistance, you know it's going to be this resistance, right? But this is not like 100 times larger than this guy. Yeah, so you can do some estimates over here. But anyway, so eventually you convert these 3 resistors into one. So you are getting an equivalent circuit like this. And you can also convert it to its Thevenin's equivalent circuit as well by doing a multiplication, right? So this will be 3 amps times this, right? And RTH is not changing. RTH is exactly the same resistance as this one. Same resistance. Any questions by far on this? No? It's pretty sweet, right? So just doing series of source transformations, you can find out the voltage at the node without doing any like a match or node voltage method. Is this helping? It's not helping with solving all the internal circuits, right? Whatever you are eventually getting is converting everything to its equivalent for the load. For the load, you are getting the voltage here, but nothing inside. So if you want to calculate anything inside, you still have to use the match or node method, right? Okay, that's the first thing you need to know. And second,
Could you use this technique on any circuit? Are there other circuits that it's not practical, possible to use this on?
yeah, DC circuits, just the DC current, DC values, no AC, no varying values like the sine wave or capacitors.
I was just saying, like, is there some way to arrange the components such that is it possible to use this? Not necessarily, but like, is there a DC circuit I could build where I could use this?
Yes. So, if you, for example, someone give you a circuit like this, right? You build it on the breadboard in the lab, and you can comfortably just convert it to this in order to drive the same load, right? It's doing the same thing to the load. No difference. It's just saving a lot of money, right? You don't have to buy so many components. It's not helping. There's so many different components. You can convert it to this. It's going to do the same thing to the load. It's not changing the effective voltage and currents to the load. Okay, now we'll move to the next method. So if you don't use a source transformation, so how do we convert the circuits into Thevenin's and Norton's equivalent circuits? This is something you have to manage, have to master. It's going to happen a lot in the semester, and I've taught circuit one for like a million of times, and there will be students at the end of the semester still don't know how to do Thevenin's equivalent circuit transformation. Okay, take the pen, do it. Grab a pen, calculate it. You'll get it in probably 2 hours, 1 hour maybe, 2 hours like that. It's not very difficult. Make sure you know how to do it, okay? Important stuff. It's 75 kilo ohms. That's a load. Whenever I draw a something like this, 2 terminals, you should know that this guy is a load. It's a load. Usually they will label as RL. So RL. 100 volts. So if you look at the Thevenin's equivalent circuit, let's do Thevenin's, don't overwhelm you guys. If you want to convert to this, so everything here, right? If you remove the load, everything here should be converted to something like this. Very simple. A voltage source in series with a resistor, okay? So now if you want to convert it to this, you need to know what this is, what this is, right? You want to calculate these two. So now let's do RTH first, RTH. So how do we do RTH? There are several steps. First, remove the load. Always, okay? First step is always remove the load. Second, short voltage source and disconnect current source. This could be the first challenge for you guys. Always get confused why we have to do that. So the voltage source has a little, almost no internal resistance. I explained that to you guys a few weeks ago, I think. Why? So this guy, the internal resistance Rin is 0, almost 0. You can consider the voltage source, the ideal voltage source has an internal resistance to be 0. Why? Since you want to deliver, the voltage source is designed that way because it's trying to deliver all the voltages to the load instead of dropping the voltage in itself. You know what I mean? So, for example, you have a voltage source, and in real world, there's a Rin, like internal resistance, for example, and you model it that way, and you remove it from the internal resistance. So now it's basically 0, right? So there's no resistance anymore. So you remove all the internal resistance to here. It's in series with the voltage source. And here's the load. So you design 5 volts power source. You want to drop all the 5 volts over here, not here. It's a voltage divider circuit, right? So the voltage 5 volts. You don't want this guy to drop any voltage. You want to drop everything here because you are supplying 5 volts to the load. That's what the customer desires, right? So what's going to happen is you have to design the power source with the internal resistance to be very close to 0, so it's not dropping anything over here. It's ideal voltage source. We're not designing a voltage source, which just let you guys know. Voltage source should be modeled as 0 internal resistance component. That's why when you are looking backwards, only look at the resistance, this one should be shorted. Short the voltage source to just replace it with a wire. However, the current source is different. You want to have a super high internal resistance, so it's able to push all the current outside. Nothing is gonna share voltage drop internally, right? So if you remember this one, right? So the other one should be disconnected. One is shorted, one is disconnected. So in that case, this circuit can be converted to this. If you are looking backwards, remove the load and looking backwards, right? The current source is disconnected. Do we have this resistor over here? Yes, it removed the load but didn't remove this one. So this one is still here. So looking backwards. So that's how you want to convert this to, by looking trying to find RTH. If I'm trying to find RTH, short this one, replace it with a wire, okay, and disconnect current source. 20 is 25K, it's 100K, 20K, 40K. Okay. Now let's look backwards. The resistance becomes what? So we got a 1 resistor here, starting from here on the top. So 130K in the main branch, and split into 2 branches. Okay, and this one comes back, and this one getting split into 2 other branches and merged over here and comes back. Always imagine that there's a current flow into it, starting from here, right? It's getting split, okay, and getting split. So the overall resistance, if you look backwards, it's 30K plus, that's the main branch. It's not in parallel with anything. So 30K plus this, right? So it's gonna be 40K in parallel with the whole thing here. 40K in parallel with the whole thing here. What's the whole thing here? That's 20K plus these 2 in parallel. 25K in parallel with 100K. That's how to find the RTH. Any questions on this? Yeah, a lot of the former students have problems with this one, looking back and find equivalent resistance. Just need more practice, okay? How to find a VTH though, VTH. First, remove the load. Second, VTH is the V out. Where's V out? If you remove this guy, you are seeing an equivalent circuit like this. Load is removed, right? 30K, because the first step is remove the load. 40K, 8 milliamps, 20K, 25K, 100K, 100 volts. So V out is over here. Have you learned how to find it? Yes, we can use many different methods to do it. Node voltage methods, mesh. Okay? Is there any current flowing through it? No. Load is removed. So V out is the same voltage here in this case. Okay? So this is VTH. VTH is found. RTH is found. Just build a circuit like this. That's the equivalent circuit. You can replace it. Replace the whole thing with this equivalent circuit. All right? Okay, we'll see you on Wednesday.
So I have a question about the last problems.
Yeah.
I tried just plugging in all the equations you gave me, and it still says it's wrong. So that means I'm definitely doing something wrong still.
Let's meet outside of the door over there since I have a class here. Meet outside of the door over there since they have a class.
Oh, okay,
Okay?
okay. Yeah.
Right.